Most of the conversation around artificial intelligence is currently centered on generative tools like chatbots and image creators. These systems are impressive, but they operate entirely within a two-dimensional space. They can write code or paint a landscape, but they lack the ability to interact with the physical world we actually live in. The real transformation is happening away from our screens, on the factory floor. Even the most sophisticated prompt is useless in a manufacturing environment if the machine receiving it cannot interpret the weight of a tool or the depth of a room. Screen-based AI provides digital answers. Solving physical, human problems requires something that can navigate three dimensions. For decades, manufacturing has relied on human workers to navigate the complex, high-stakes environments of an assembly line. While we have used robotics for years, these older systems rely on rigid, pre-programmed code. A traditional robotic arm follows a specific path over and over. It doesn't actually understand its environment. It simply executes a series of fixed coordinates. Because these machines lack spatial awareness, they cannot adapt to a part being out of place or a person walking into their path. This means humans must still perform the most unpredictable and dangerous work. Building hardware today without integrating generative cognition continues to place the physical risk of heavy industry on human workers. Solving this requires a merger of mechanical engineering with advanced artificial intelligence. The primary challenge here is contextual translation. We have to bridge the gap between a machine's digital instructions and its physical movements. We use embodied AI, powered by vision language action, or VLA models. It starts with language, parsing a human's intent. That passes to the vision node, interpreting the physical geometry of its surroundings. Finally, the action node uses those constraints to plan a safe, autonomous movement. A VLA model provides a machine with a complete cognitive architecture, giving it the spatial awareness needed to function in a changing environment. Training a chatbot to be empathetic is a matter of language patterns. Operating heavy machinery is a matter of life and death. Embodied AI must constantly calculate variables like gravity, material resistance, and the physics of a collision. This real-time spatial calculation distinguishes generative cognition from simple automation. The machine adapts its behavior based on the physical laws of the room. While digital communication is a solved problem, navigating a physical space safely requires a specialized class of engineering. Artificial intelligence proves its value by successfully predicting and manipulating the physical world around it. The primary goal of this technology is to remove human vulnerability from industrial settings. Humans are still required to handle live explosives and perform high-heat welding because traditional robots lack the awareness to do so safely. Embodied AI provides a way to delegate these unpredictable, high-risk tasks to machines that can see and react to danger. This integration of generative cognition into hardware is the core of Industry 5.0. Industry 5.0 is a manufacturing model that prioritizes the safety and well-being of the human worker. Transitioning to these autonomous systems is a necessary step to protect human life in the most dangerous environments. There is a common concern that the aim of advanced AI is to replace all human effort. But building industrial hardware with cognitive abilities is more about addressing physical risk than simply generating digital content. When we create machines capable of handling live explosives or heavy manufacturing, we are using technology to address the hazards humans have faced for over a century. By moving past the era of the screen, we can focus our innovation on physical systems that prioritize human safety.